Well, I guess I'm recording. Good morning, ladies and gentlemen. My computer is just taking a little slow this morning. First off, go Bears, big game last night. Second of all, I guess I've got the Rona. Yeah, but as you can tell, so far I'm doing fine. I hope you all are doing fine. Of course, as soon as I say that, I do that. Trust me, that's a normal everyday occurrence right there for me. Anyway, I'm going to do a short and sweet video that corresponds with what you have going out for assignments today. Next week, again, as you've already discussed, it's going to be a little weird. And I'm going to be stuck here. So I'm going to do my best and try not to blind you all in here. With what I've got so far, I might have to ask somebody to get some stuff for me from school, but we'll get that done. Anyway, I don't want to take up any more of your time, so let's go ahead and continue working on Chapter 3. Now, Section 2, we're looking at vector operations. And in the first section, as you're going to see here shortly, we talked about how we can graphically solve vectors. And if you hopefully watched the video I did on that earlier this week, and you saw, at least with my setup, how difficult it can be. And there are some shortcomings with trying to do it graphically. And as you saw in the videos, a lot of it was just trying to make sure the scale was right and then getting all the angles right and all this nonsense. And so we'll talk a little more about that here in a little bit. But for section 2, we are going to be identifying appropriate coordinate systems for solving problems with vectors. We're going to apply the Pythagorean theorem. I think y'all know what that is. And tangent function to calculate the magnitude and direction of a resultant vector. We will then resolve vectors into components using the sine and cosine functions. And lastly, we're going to add vectors that are not perpendicular. Not going to lie, that's the fun one. Okay, so let's get started with the short discussion we're going to have today. So if you recall, the name of the chapter is essentially motion in 2 dimensions. And so we are going to be essentially assigning coordinate systems in 2 dimensions to help us describe the motion of objects. And so one of the best ways to do that is to use the X and Y axis. Okay. This is because they are fixed, and it helps us give a general sense of direction of objects in motion. So what we need to consider is that the y-axis, the north positioning of the y-axis would be positive, as well as the x-axis to the east. And it's going to be the opposite for the y-axis to the south and the x-axis to the west. We've seen this in the first chapter, or sorry, chapter 2, where we determine signage, positive or negative, to determine overall direction. So that's what we're going to continue that practice here. So as I mentioned in the first section, we determined this stuff graphically, and with my setup, it was done pretty poorly. I'm not going to lie. I'm not going to sugarcoat it. It could have been better, given, other circumstances, absolutely. But one of the things I also forgot to do was, once I got my resultant vector determined, was I needed to use my protractor to then determine the overall angle of our resultant vector. And see, that's something that you can forget to do when you are trying to do everything graphically. And with graphically, other than forgetting to do the protractor and making sure you have your scales right, you also have to make sure that your vectors are drawn exactly to the T as to the values assigned to each one of them. And if you don't do that right, you're not going to be 100% correct. So one of the easiest things to do is use the Pythagorean theorem and the tangent function. And I have the asterisk of tangent function because sometimes, I would say the majority of the time, you are going to use a tangent function, okay? A few percentage of the other times, it just depends on what angle you're trying to figure out, or what vector you're trying to figure out. And then you might have to adjust and use the other trig functions that we just mentioned in the previous slide. So we can use the Pythagorean theorem to find the magnitude of the resultant vector. Now, this only works when we have right triangles, as you may know. So when we start getting into triangles that are not perpendicular to each other, then we have to come up with other choices, which we'll talk about that next weekish. Anyway, so next formula to write on your formula sheet here is Pythagorean theorem. Why not? I know you know it, but hey, might as well add it, right? Anyway, a squared plus b squared equals c squared. Simple enough. All right. Let's go ahead and use it here in just a minute. Next is a tangent function, okay? You're going to use the tangent function to find the direction of the resultant vector. For any right triangle, the tangent function of the angle is defined as the ratio of the opposite and adjacent legs with respect to a specified acute angle of a right triangle. Anyway, here's the next formula you can write down there. Tangent of angle theta. Don't forget that. Oh, wait, that's not what I want. Sorry. I'm doing this from my home computer, and actually I'm doing it from my Chromebook at home, and I'm not used to it. It doesn't give me all the options I want. Anyway, tangent of angle theta. That little guy right there, if you don't remember, that is theta, equals opposite leg over adjacent leg. You notice that theta is usually going to be the angle from which an object has the originating location of our object in motion. Okay, a lot of times it's where the x and y axis come together, the origin. Okay, so one thing we're going to see here when we do our practice question is this tangent of angle theta. These are, you can almost think of these as two different entities. Okay, almost like if you said like 2x. Okay, that's just an example where you have the tangent of angle theta, where tangent of angle and theta are two different entities. And so when we go and solve for theta, we have to take the inverse of the tangent function, which is on your calculator, and move it over to the opposite side of this equal sign here. So we're going to see that here in our first practice deal. There we go. So we have an archaeologist climbs the Great Pyramid in Giza. Remember how the shape of a pyramid is. It's a triangle, three-dimensional triangle. The pyramid's height is 136 meters, and its width is 2.30 times 10 to the second meters, or as we call it, 230 meters. What is the magnitude and the direction of the displacement of the archaeologist? Sorry, that's a tongue twister this early in the morning. Archaeologist, after she has climbed from the top, still early, from the bottom of the pyramid to the top. My eyes are getting ahead of my mouth here. All right, so let's list the things that we know. Okay, we know that the height at the highest point, which we would expect to be the point of the triangle or the pyramid, is 136 meters. Now the width, we were told, is 230 meters from end to end. However, we can split that in half and make a right triangle. So really, the pyramid's going to come all the way down here. It's going to have the second half here. But in order for us to use the Pythagorean theorem and everything like that, all we are concerned about is making this a right triangle. So we need to know the basically the displacement, the magnitude, and direction. So we need to know the overall distance that was traveled and what exact direction it was. So we need to figure our d, which is our hypotenuse, and our theta. So again, setting up a coordinate system. Again, using the two formulas here, the Pythagorean theorem and the tangent of theta, rearranging to solve for d. Again, you can't solve for the hypotenuse when it's squared, so you have to take the square root of your x squared and your y squared. Now, don't automatically say that, well, if I'm taking the square root of this in both sides, that these can get eliminated. They won't, okay? Just keep them as is, solve them as they normally are, and then you can take the square root of them, okay? And then over here is where I was talking about, okay? In order to find the actual theta, you have to take the inverse tangent and put that to both sides, all right? So solve for your opposite divided by adjacent, and then take the inverse tangent of that result, okay? So let's look at putting everything in here. So we put our x value or x magnitude in here, and we put our y magnitude in here. Don't forget to square them, then sum them up, then take the square root. So as you can see here, if you were just to remove those square roots from here, the squares when you did the square root, you would not get the correct answer. Because if you just add 115 plus 136, you do not get 178. So square them both, add them up, then take the square root. Next, we are going to take the values for the x and y coordinates. So again, the y coordinate was the height of the pyramid, 136 meters, divided by 115 meters. There's a meters missing there. Once you've taken that, you then take the inverse tangent function, and you find that the angle at which the archaeologist took from her origin was 49.8 degrees. So that gives you an idea of exactly how steep or not steep the angle was. So she's actually going just beyond halfway vertical. So that's pretty steep. All right. So now we know exactly how far she traveled from the base of the pyramid to the top, and exactly at how she did it, at what angle. So that's what vectors are going to do for us. We're giving us some very specifics regarding, angles, approaches, distances, all that good stuff. So anyway, you can evaluate it down here. It says because d is the hypotenuse, the archaeologist's displacement should be less than the sum of the height and half of the width. Okay, so just saying if we were to sum this up, the hypotenuse or our overall displacement, our resultant vector should be less than the height and the half the width. Okay, and it's expected the angle is expected to be 45 degrees or more than, because the height is greater than half the width. Okay, those are ways to check it. You don't have to check it that way, but eventually we're also going to get to the point where we might say that the angle that was taken was 49.8 degrees above the horizontal or above the horizon. So we're going to get even more specific as we move along in here. But that actually wraps up this. And I'm sorry this is a short video, and I'm sorry that I don't have time to do the practice examples like I would normally do. That's what I had planned for today. But I have a few things that I need to gather moving forward. So if you have any questions regarding your homework tonight, feel free to contact me. I'm not going anywhere for a while here. I'm kind of stuck. So anyway, I hope everyone's doing well. I hate this. I wish I was there with you. But I'll try to see you as much as I can over the next 10 days or so, even though it may be virtual. Keep an eye on the Google Classroom. Probably going to be making some changes here in the next couple of days, but I'll definitely keep you informed. All right, and with that being said, I'm going to go ahead and end the video, and get a hold of me if you've got any questions. Bye, kids. Maybe I can't get my computer to work. There we go.